You are sitting at a red light, the car is not moving, the wheels are not turning, you are going nowhere. And yet, right in front of you, under a sheet of metal, hundreds of parts are still moving at terrifying speed. Pistons are still rising and falling. Valves are still opening and closing. Fuel is still being sprayed. Spark plugs are still firing. Belts are still spinning. Oil is still being pumped. Coolant is still circulating. Air is still being compressed. Electricity is still being generated. And all of that is happening just so your car can do apparently nothing, which raises a very reasonable question. Why does a car engine keep running even when the car is standing still? Why doesn't it just stop? After all, if the whole purpose of an engine is to move the car, then the moment the car stops moving, shouldn't the engine stop too? And today that question matters even more because some cars actually do shut off at traffic lights. So if modern cars can stop and restart automatically, why did cars spend more than a century idling at every stop sign, traffic jam, railroad crossing, and drive-through lane on Earth? The answer is far more interesting than that's just how cars work. Because a standing car is not actually doing nothing. Even when it looks motionless from the outside, the car is still trying to stay alive on the inside. Welcome to Simple Concepts Explained. Today we are pulling back the curtain on why car engines keep running when the vehicle is standing still. And to understand that, we need to start with one of the biggest misconceptions in everyday driving. Most people think the engine only exists to turn the wheels. It doesn't. That is only the most visible job. In a traditional car, the engine is not just a source of motion. It is the center of an entire ecosystem. The moment the engine starts, it begins feeding multiple systems that the rest of the vehicle depends on. Some of those systems help move the car, some help cool it, some help steer it, some help stop it, some help power comfort features people now take for granted, and some are needed simply to prevent the engine from destroying itself. That is where the logic of idling begins. Because when the car stops moving, those needs do not instantly disappear. The first thing to understand is this. A conventional gasoline or diesel car was historically designed around the assumption that if the engine is on, everything important can be supplied, and if the engine is off, many of those supports either weaken, pause, or disappear. Let's start with the most obvious one, electricity. A lot of people assume the battery runs the car's electronics all the time. It doesn't. Not in the way most people imagine. In a normal combustion vehicle, the battery mainly starts the engine and stabilizes the electrical system. Once the engine is running, the alternator takes over a huge part of the electrical work. It is driven by the crankshaft, usually through a serpentine belt, and it generates power for the lights, dashboard, electronics, and charging system while also recharging the battery. That means if you are sitting at a traffic light with the headlights on, the blower fan running, the infotainment screen glowing, the rear defroster active, the phone charging, and the wipers moving, a traditional car is not casually sipping battery power like a flashlight. It is depending on an engine-driven charging system, and the moment you shut the engine off, that arrangement changes. Now the battery must carry the load. For a short time, that is fine. For repeated stops all day long, that becomes a design problem. That is exactly why stop-start systems needed upgraded hardware before they could go mainstream. Ford says auto start-stop may not shut the engine off when the battery is charging, the engine is still warming up, or when heat and air conditioning are being used, and notes that these vehicles use a heavy-duty starter and battery. AAA similarly notes that when the engine shuts off, the battery must carry lights, climate control, infotainment, charging ports, and other electrical loads. So the first hidden answer is simple. Historically, engines kept running at a stop because the car still needed a live power plant. But electricity is only part of the story, because even if you could somehow keep all the electronics alive with a battery, a traditional engine-driven car still has several mechanical systems that were never meant to function for long with the engine stopped. Take cooling. A car engine is an organized explosion machine. Every second it runs, it produces enormous heat. That heat has to be controlled, or the engine damages itself. In traditional layouts, the water pump that moves coolant through the engine is belt-driven. It uses mechanical energy from the engine to circulate coolant through the block and radiator. If that pumping action stops at the wrong moment, heat can build where you do not want it. How Stuff Works notes that the traditional water pump is typically belt-driven, while electric water pumps were developed partly to avoid the constant dependence on engine belt power. Now here is where people often push back. They say, but if I'm stopped at a light, the engine is barely doing any work. That is true. But the engine is still hot, sometimes very hot. If you have just come off a highway, climbed a hill, sat in summer traffic, or been using the air conditioner hard, the engine compartment may be carrying a lot of residual heat. Traditional vehicles were built around the idea that as long as the engine continues to idle, coolant continues to circulate, oil continues to move, and the thermal system remains stable. Shut the engine off and you suddenly break that flow. Modern cars can manage this far better, but older combustion layouts were much more comfortable just staying on. Then we arrive at the heart of the engine itself, lubrication. If there is one system a running engine cannot afford to lose, it is oil pressure. The oil pump is the heart of the lubrication system. It sucks oil from the sump and forces it through the engine's oil ways, so bearings, moving surfaces, and high-friction components stay separated by a protective film. On most engines, the oil pump is driven directly by the crankshaft, which means that if the engine is turning, the pump is working. If the engine stops, that pumping action stops too. That matters because idling is not just wasting fuel. It is also the condition under which the engine keeps its internal circulation alive. At idle, the engine is maintaining combustion, oil pressure, coolant flow, charging capacity, and support for attached accessories. It is the minimum effort required to keep the whole machine awake. And that helps explain something important. A stationary car with the engine running is not inactive. It is in a kind of standby mode, not asleep, not fully working, but ready. And readiness is everything in a car. Because the driver does not want to wait 5 or 10 seconds every time the traffic light changes. The driver wants this: foot off brake, foot on gas, move now. That instant response shaped car engineering for generations. The engine idles because the car is waiting for a command. But even that still is not the full answer. Because some of the most important hidden systems are not just about keeping the engine alive. They are about helping the driver control the car. Let's take power steering. In many older and conventional vehicles, hydraulic power steering relies on a pump driven by the engine. That pump is usually turned by a belt from the crankshaft. If the engine is not running, the hydraulic assist disappears and steering becomes much heavier. Now imagine creeping through a parking garage, waiting at an intersection preparing for a quick turn, or edging forward in traffic. You may not be accelerating, but you still expect light, easy steering. That expectation only works if assist is available. In modern cars, electric power steering changed a lot of this, but for decades, engine on meant steering assist available right now. Then there are the brakes. Most drivers have no idea how much easier modern braking feels because of power assist. The brake booster in many gasoline cars uses engine vacuum to multiply the force from your foot. How stuff works explains that the engine provides the vacuum source and a check valve preserves some reserve assist if the engine stops, but only for a limited number of stops. Diesel vehicles often need separate vacuum pumps because the engine does not naturally supply that vacuum in the same way. That line matters. Reserve assist, not permanent assist. Reserve. So yes, if an engine dies, the car does not instantly become unbreakable. But the car is no longer operating in its preferred state. The assist begins becoming a limited resource. Again, modern systems have evolved. But historically, if you wanted the car fully ready to move, steer, and stop as designed, the easiest answer was to keep the engine idling. And then there is comfort, which sounds trivial until it isn't. Air conditioning in a traditional car depends on a compressor that is driven by a belt attached to the engine's crankshaft. In other words, no spinning engine usually means no belt-driven AC compressor. That is why stop-start systems often decide not to shut the engine off in certain conditions. Ford explicitly says the system may keep the engine running if heat or air conditioning is being used. Honda's auto-idle stop documentation lists battery temperature, climate control demand, outside temperature, coolant temperature, transmission temperature, cabin conditions, and fan use among the reasons the system may not activate or may restart the engine while the car is stopped. That gives away the deeper truth. Cars did not idle for so long because engineers forgot engines could be turned off. They idled because keeping a car comfortable, responsive, electrically stable, lubricated, cooled, steerable, and brake-ready was much easier if the engine just kept spinning. Now we get to the part most people assume is the main reason. Starting the engine used to be more annoying than keeping it on. And for a long time, that was true. Today, people live with stop-start systems so often that the restart feels normal. But for most of automotive history, repeatedly shutting the engine down at every stop would have been intrusive, harder on hardware, slower, and more noticeable. You would hear it, feel it, wait for it. And if the battery was weak, the weather was cold, or the engine was temperamental, you might not get the quick restart you wanted. This is one reason stop-start systems required stronger components. Ford mentions a heavy-duty starter and battery. AAA notes that the repeated restarts can number in the hundreds per day and therefore require more battery capability than traditional setups. So for decades, idling was the simplest engineering compromise. Burn a little fuel, keep the whole system alive, stay ready to move. Avoid repeated start events, preserve comfort. Preserve response, avoid complexity. That logic was so normal that drivers barely noticed it. They sat in a queue. The engine ran. That was just what a car did. But then fuel economy standards tightened. Traffic got worse, cities got denser, idle emissions mattered more, and the old logic started to look expensive, because a car at idle is still burning fuel while delivering 0 miles per gallon. The U.S. Department of Energy's Alternative Fuels Data Center says the basic idle reduction rule for personal vehicles is to turn the engine off when parked or stopped for more than 10 seconds, except in traffic. A How Stuff Works article citing Natural Resources Canada says idling for more than 10 seconds can use more fuel than restarting the engine. That is the moment the story flips. For most of automotive history, the question was, how do we keep the car happily alive at a stop? Now the question became, how do we keep all the important functions alive without wasting fuel by idling? That is exactly what stop-start technology is trying to solve. Not by pretending the old reasons for idling were fake, but by engineering around them. Modern stop-start systems are basically an admission that the old car really did need many of those supports. The difference is that newer cars can now replicate them more intelligently. The battery is upgraded, the starter is stronger, the control software is smarter, the car monitors temperature, charge level, steering input, climate demand, and operating conditions. Then it decides, shut off, stay on, or restart right now. In other words, the car is constantly asking a hidden question. Can I afford to go to sleep for a moment without the driver noticing a loss? If yes, it shuts off. If no, it keeps idling. That is why these systems do not operate every single time. Honda's documentation shows just how conditional the decision is. Low or high coolant temperature, low battery charge, very cold battery temperature, heavy climate control demand, high fan speed, steering wheel movement, steep inclines, sudden stops, large cabin temperature differences, and other conditions can all prevent auto idle stop or trigger a restart. That one detail tells you everything. A stopped car is still a living machine with ongoing needs. If those needs are light, the engine can go quiet. If those needs are high, the engine stays awake. And that leads to an even better version of the original question. Not, why does the engine run while standing still? But, what jobs are still being done when the car is standing still? The answer is, more than most people realize. Sometimes the engine is charging the battery, sometimes it is keeping the AC compressor available, sometimes it is maintaining thermal stability, sometimes it is preserving oil circulation. Sometimes it is supporting hydraulic or vacuum-based assist systems. Sometimes it is preparing for an immediate launch. Sometimes it is doing several of those at once. And sometimes, especially in newer cars, the engine is off specifically because the car has enough alternate capability to survive that pause. Now, there is another misconception worth killing. A lot of people think stop-start technology proves idling was always unnecessary. It doesn't. It proves that technology evolved enough to make idling less necessary under certain conditions. That is not the same thing. A traditional car from 30 years ago, a base economy car from the early 2000s, a new stop-start crossover, and a hybrid all answer the stopped at a light problem differently. An older car says, keep the engine running because that is the simplest way to keep the machine fully ready. A stop-start car says, I can shut down briefly, but only if charge, climate, temperature, and control conditions are favorable. A hybrid says, I have enough electric architecture to keep many functions alive while using the engine only when needed. And an EV says, I do not have this problem at all because propulsion and accessory architecture are fundamentally different. That is why the title of this topic feels true in everyday life, even though it is not universally true anymore. Because for over a century, the default behavior of the car was, if the car is on, the engine stays on. What we are living through now is the breakdown of that rule. And it is happening because cars are slowly being redesigned away from mechanical dependence on a constantly spinning engine. Look at the list of old dependencies. Alternator, engine-driven. Water pump, traditionally engine-driven. A C compressor, traditionally engine-driven. Power steering pump, often engine-driven. Brake booster vacuum, often engine-provided. Oil pump, directly tied to engine rotation. Serpentine belt, the mechanical highway connecting crankshaft motion to many support systems. Now compare that with newer trends. Electric power steering reduces dependence on engine-driven hydraulics. Electric coolant pumps can circulate coolant without belt power. More advanced electrical systems can carry accessory loads during short engine-off windows. Hybrids can run climate and low-speed functions differently. The engine is no longer the only heart in the body. It is becoming one organ in a broader network. And as soon as that happens, the car gains the freedom to stop the engine more often. But not because the engine was pointless while idling, because other systems have finally become strong enough to cover for it. There is also a human factor here. Drivers hate hesitation, even tiny hesitation. If the light turns green and the car delays, drivers notice. If the cabin suddenly gets warmer, drivers notice. If the steering feels different, drivers notice. If the restart shudders, drivers notice. So engineers had to build stop-start in a way that preserved the illusion that nothing important was lost. That is why the systems are so conservative. That is why some drivers feel the engine didn't stop when they expected it to, because the car is protecting priorities the driver cannot see: battery charge, temperature, climate demand, steering input, restart confidence, system stability. Those invisible priorities are the modern version of the same old rule. A standing car still has work to do, and if turning the engine off threatens that work, the engine keeps running. Then there is the emissions angle. This is where the logic gets almost philosophical. Historically, idling was accepted because it was simple and reliable, but simple and reliable does not always mean efficient. AAA's testing found automatic stop-start systems improved fuel economy by roughly 5 to 7% in the tested urban cycle. That is significant for a change the driver barely controls manually. So now engineers are trapped between two truths. Truth number one: a conventional car wants the engine running so all the traditional support systems remain available. Truth number two: a stopped car burning fuel to do that is inefficient. Stop-start systems are the negotiated peace treaty between those truths. They are not a rejection of idling. They are a smarter form of it. The car idles when it needs to. It goes silent when it can. And that means the real answer to our title is surprisingly elegant. Car engines used to run while the car was standing still because the car was never truly standing still in mechanical terms. The body was motionless. The machine was not. The engine was generating power, turning pumps, sustaining pressure, preserving assist, supporting comfort, and waiting for instant movement. It was not running for no reason. It was holding the system together. That is also why the transition away from constant idling has taken so long. You're not just changing a habit, you're changing an architecture. You are moving from a world where everything depends on one spinning shaft to a world where more and more support functions can survive independently. That sounds small. It is not. It is one of the quietest revolutions in the modern automobile, because when a new car smoothly shuts off at a red light and restarts the instant you lift your foot, what you are witnessing is not just a fuel-saving trick. You are witnessing a machine that has learned how to briefly suspend its heart without collapsing the rest of its body. That is what older cars could not do, and that is why they idled. Not because engineers were lazy, not because nobody thought to switch the engine off, and not because the engine was somehow wasting time. They idled because a conventional car was built around a simple rule. If the engine is alive, the whole car is supported. If the engine goes quiet, too many essential systems begin depending on finite reserves, reduced assist, or alternate hardware the car may not have. So the engine keeps running, even while parked, even at a light, even in traffic, even when the car appears to be doing absolutely nothing. Because from the car's point of view, it is doing exactly what it must do, staying ready. And that is the detail most people never see. When you sit at a red light and hear that soft, steady idle, you are not listening to wasted motion. You are listening to a machine holding electrical load, thermal balance, lubrication flow, system pressure, cabin comfort, and instant readiness all at once. You are listening to the hidden cost of keeping a traditional car prepared for the next second. And once you see it that way, the whole thing changes. The idling engine no longer looks pointless. It looks like a support system. A mechanical life support loop, a compromise between comfort, control, readiness, and engineering tradition. So the next time you stop at an intersection and the car beside you sits there humming quietly, remember? That engine is not just waiting for the light to turn green. It is keeping an entire machine awake. And that is why, for most of automotive history, car engines kept running even when the car was standing still.